A very good welcome to Dr. Cooley Chain. Our group would like to present about analysis and application of pulse modulation technique. Our group member is Alia Shafa binti Syami, Rafidah binti Bidin, Veroni Ramos anak Gilas Gana, Muhammad Farhan bin Muhammad Taufik, and Takif Muntaza bin Ismail.
Hello, my name is Takif Muntaza bin Ismail. My metric number is 101207. Today, I will be discussing pulse code modulation or PCM. PCM is a method used to convert analog signals into digital form. This is done through three main steps: sampling, quantizing, and encoding. The result is a digital signal made up of a binary sequence consisting of ones and zeros. Now, let's break this down further. Starting with the working principle. PCM works by taking an analog signal and transforming it into digital pulses. It does this by sampling the signal at regular intervals, quantizing the sample value into discrete levels, and then encoding those levels into binary code. Looking at the signal output, as I just mentioned, the final result is a series of binary numbers, basically just ones and zeros, which can be transmitted over a digital system. As for advantages of PCM, it helps reduce transmission losses and eliminates noise and interference, making it ideal for long-distance communication. However, disadvantage is that PCM is more complex than analog modulation techniques. It requires more processing power and bandwidth to handle the digital data.
Pulse width modulation, commonly known as PWM. This is a very common technique used across various electronic applications, from controlling motor speeds to dimming LED lights. For the working principle, PWM controls the average output by varying the on-time or pulse width of a fixed frequency signal. This is typically achieved using a comparator that compares a modulating signal with a sawtooth or triangular wave. The point at which these two signals intersect determines the width of the resulting pulse. The signal output of PWM consists of fixed frequency pulses, but with a varying duty cycle. The duty cycle refers to the proportion of on-time within a single period pulse. By changing this on-time, we effectively change the power delivered. For the advantages of PWM, first, it is highly cost-efficient to implement, which makes it a popular choice in many designs. Second, it is remarkably energy efficient. Because of the switching components are either fully on or fully off, they dissipate very little power as heat, which leads to less energy waste. Third is it allows for precise control of average voltage, which make it ideal for application requiring fine-tuned power delivery. However, PWM also has its advantages. It can sometimes require complex circuits for high precision or noise filtering. Additionally, the rapid switching involved in PWM can produce unwanted acoustic noise, which might be a concern in certain environments with specific types of loads, such as motors. Delta modulation, often abbreviated as DM, is a powerful method using to convert analog signal into a 1-bit digital stream. It is a simpler alternative to more complex modulation schemes and has its own set of advantages and disadvantages. The working principle of delta modulation is it converts an analog signal into a 1-bit digital stream by continuously assessing whether the analog signal is increasing or decreasing. This is achieved using a simple 1-bit quantizer. The resulting signal output is a 1-bit bit stream. 1 in this bit stream signifies an increase, where a 0 signifies a decrease in the analog signal. As this 1 and 0 accumulate, they form a staircase approximation of the original analog signal. However, DM isn't about its limitation. One of the drawbacks is that it's prone to slope overload distortion. This occurs when the analog signal changes too fast for the modulator to keep up, leading to a poor approximation. Conversely, if the signal changes too slow, it can suffer from granular noise, where the step size is too large for the gradual changes. Despite these challenges, delta modulation offers several compelling advantages. Its primary strength lies in the simplicity. It's much simpler to implement compared to more complex modulation techniques. It's also robust against noise, making it reliable in various transmission environments. Lastly, it boasts a lower signaling rate and transmission bandwidth compared to pulse code modulation (PCM).
So in this design, we have choose pulse code modulation (PCM) as the pulse modulation technique to solve the problems in telemedicine. In telemedicine, real-time voice communication between healthcare providers and patients must be accurate and immune to noise. Analog signals are highly susceptible to degradation during transmission. Thus, PCM provides a solution by converting. So the first design process is analog signal generation. In this design, we use MATLAB to create the PCM. So sinusoidal signal was created using the function x equals to sine 2 pi times f times t with the frequency of 5 Hz and amplitude of 1. This analog signal represents real-world analog signal, which is audio tone or human voice. At the same time, this analog signal will be the input signal which to be digitized using PCM. The next design process is parameter declaration. In this design of PCM, we have set the sampling frequency Fs equals to 1000 Hz, which meets the Nyquist rate Fs greater or equals to 2f. Next, we have declared the time vector and quantization levels to level 8 PCM and level 16 PCM to compare the performance of this PCM. Next, we have declared the step size Q, signal power, bits per sample to be computed. So this is the source code of the PCM that was created using MATLAB. The next step is to simulate the code in MATLAB. So in this simulation, it shows the original analog signal in 2 cycles, the quantized signal with level 8, and original versus reconstructed signal for level 8, and the bit stream for level 8 PCM. So next, this is the quantized signal of level 16 PCM with its original versus reconstructed signal of level 6 PCM and its bit stream.
Here we can see the original analog sine wave and its quantized version using 8-level PCM. Notice the staircase effect caused by limited quantization levels, which leads to visible distortion and larger quantization steps. In comparison, the 16-level PCM produces a much smoother approximation of the original analog waveform. The reconstructed signal closely follows the original, thanks to smaller step size and better resolution. Here are the bit streams for both 8-level and 16-level PCM. The 8-level system uses 3 bits per sample, while the 16-level uses 4 bits per sample. While the 16-level streams require more data, it provides higher signal fidelity. In pulse code modulation, bandwidth increases with the number of bits used per sample. Higher quantization levels, such as in 16-level PCM, require more bits to represent each sample compared to 8-level PCM. This leads to a higher bit rate, hence a greater bandwidth requirement. Although this consumes more transmission resources, it results in better signal accuracy and higher signal-to-noise ratio. Therefore, there is a direct trade-off.
Larger bandwidth enable improved signal fidelity, but at a cost of increased data transmission needs.
In this project, we focus on three pulse modulation techniques, which are pulse chord modulation, pulse width modulation, and delta modulation. Only pulse chord modulation was simulated using MATLAB. We use it to convert an analog signal into a digital signal and then reconstructed it. We compare 8-level and 16-level pulse chord modulation, where 16-level provide a better accuracy and a higher signal to quantization noise ratio, increasing from 18.76 decibel to 22.88 decibel. For pulse width modulation and delta modulation, we only explore them theoretically. Pulse chord modulation is accurate but more complex. Pulse width modulation is efficient but may cause noise, and delta modulation is simple but less accurate without adaptation.